All right, in this little video, we're going to take a look at scientific notation. It doesn't have to be that bad, but we're going to take a couple of real-life examples. And when I say real life, I mean, no, it's scientific notation. We're going to create science examples. Easiest way to do this. Woo, that's not what I wanted, but we'll work with it. Easiest way to work with this is to count the number of times you move a decimal place. My dog decided that now she wanted my attention, of course. So let's take a couple of constants that some of you may be familiar with, others perhaps not. We have guacamole's number. Okay, so it's not really guacamole's number, but that's the way I remember it, because I remember that guacamole is made from avocados, and it sounds like Avogadro. This is truly Avogadro's number. And I'm going to probably spell his name wrong. Avogadro. God with the... There you go. R-O. It's close enough. So this is Avogadro's constant. This stands for the number of elements, especially atoms, in a mole of a substance. But it's not limited to atoms. It's also... you can do molecules in a mole. So if you had a diatomic molecule, say nitrogen, then it's actually 2 Avogadro numbers worth of atoms, because it's the number of nitrogen molecules in a mole of nitrogen. So this is where I get, for all you chemistry gurus out there, that's where I get my mole from. So guacamole's number is roughly 6.022 times 10 to the 23rd. This is why it's celebrated on October 23rd of every year. So if I wanted to write that out as a complete number, it's kind of terrible, to be honest. It's 022. I have to move this decimal place. This is, first of all, let's kind of explain where we sit with this. The number in front here starts the number of the scientific notation. So the decimal and the scientific notation both start the same way. The difference is this. And you can argue with me, it's the numerical accuracy of this, because it goes on for a few more decimal places, but this is close enough. In order to write this in such a small looking number, I actually had to divide by a lot. Well, I can't divide by a lot without going ahead and remultiplying. That's what this piece does. It says, okay, I've shrunk the number by this amount, so I have to make it bigger by that amount. To get that number, what we do is we start with the decimal place and we move it bigger. Positive exponents on the 10 mean we have really large numbers, and so we have to make this number bigger. I don't do the left and right thing. I do bigger, smaller, because, well, it seems to make more sense. So 1, 2, 3. Well, I've gone 3. All right, we only got 20 more to go. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And 1, 2, 3, 4, 5. Okay, now we just fill in the zeros wherever you see a blank spot. Oh, so many zeros. So many zeros indeed. I don't like the placement of that 0. Let's go here and here. Okay. Now, if we break them up into periods, so every 3 we throw a comma. If I remember correctly, in Britain they throw a decimal and they put a comma where our decimal is. But every 3 represent a period, and so we... Well, that's not too bad. So here we have the ones, the thousands, the millions, the billions, the trillions, the quadrillions, the quintillions, and the sextillions. So this is a 602 sextillion and 200 quintillion. Very important that you know the size of these numbers, because we don't want to work with them. So rather than type all that crap out every time you want to use an Avogadro number of things, or counting the number of moles on a witch's face, or I don't know, wherever you would like to use Avogadro's number, you want to write this out every single time? Ew. Yuck. All right, so we can shorten it up, and to shorten it, you work the same way. If this was your number, this was your decimal point right here, you just simply move it until you have a number between 1 and 10. Has to be strictly less than 10, but it can be 1. So this number right here, the number that we have in front, wants to be between 1 and 10. That's the rule for scientific notation. All right, so let's show you one where we go small. So here's a chemistry version for y'all. Now we can go to physics and we can talk about the ultra tiny. And so we talk about Planck's constant. Planck's, I'm probably going to spell his name wrong too, because I think there's an H in there somewhere. I want to say that's like an H right there at the end. But Planck's constant. And it is 6.626. The other 6, the kind that looks like a 6, times 10 to the negative 34 joule seconds. That's important. Don't ever forget Planck's constant. Anyway, this occurs in, well, you can call it in particle physics, but essentially the Planck's constant refers to the amount of energy contained in one quanta of light, so one photon of light, and kind of refers to the amount of energy that you have in just that little packet. This can also be converted, as I've read in other places, they apparently use this as well to standardize the kilogram recently, where it used to be this big, huge thing of platinum and uridium alloy is now kind of rusting and not accurate anymore, so they wanted to abstract the value of the kilogram, and this is how they're doing it, I guess. Good for them. So I'm going to start way over here. 6.626, and I have to move 34. Now the negative here, this guy means I'm a small number, not I'm a negative number. That is not what it implies. It implies I'm a small number. So you can think of it this way: if you have your exponent rules from math, you'll know that 10 to the wow, brain is not functional today. 10 to the negative 34 is really 1 over 10 to the 34. So we really need to take 10 and raise it to the 34th power, which is going to give us a whole lot of zeros. But notice it doesn't change the sign of the number. It changes whether it's big or small. So the negative will imply a small number. So we have to move this baby smaller. So it's going to add zeros to the left side of it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. You can see my hands already getting tired. 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34. Oh, finally there. Here's a 0. I'll let you do the work. You can see that working with this would just be terrible. I mean, seriously. I had 33 zeros before I hit a number that's worthwhile. Hence the reason for scientific notation. From a purely mathematical standpoint, this is nothing more than use of the exponent rules that we're well aware of in the real number system. Those exponent rules will extend into different number systems. They might not all hold true for all number systems, though. So just to keep that in mind. From a mathematical perspective, this is just kind of like, that's kind of nice. But to scientists, this is everything, because now I don't have to put all that crap into a calculator. Now I can do this. So how do I put this into a calculator that will allow for scientific notation? Great. They all kind of tend to work the same way. This is Texas Instruments TI-84 Silver Series. The color will work the same way. The 83 will work the same way. The 84 and the 84 Plus and the 83 Plus will all work the same way for this. The vast majority of the TI calculators will tend to work this way. Every calculator will have this button somewhere. The scientific calculators will have it on the button face because it's used a lot, hence scientific calculator. So if I wanted to put Avogadro's number in there, then I would put in 6.022, and now I need the times 10 to the button. Wherever you have this button right here, you'll have an EE button. Not to be confused with the E button, because E is an actual number, but you usually have a double capital E, and this stands for times 10 to the... It's all one word. You have to say it really fast. So I put in my initial digits, and then I say times 10 to the, which is, in the case of the TI, it's the second key plus the comma. Notice the double E. I wish I had a zoom feature. If I knew how to work my recording software better, maybe I could. But I have this little double E right here on the comma, just above the 7, and I have to apply the second button in order to get to it. On my screen, it'll put this little E thing. Now, on some calculators, you might not get the E, but you'll get a kind of a space or maybe like a slight superscript. It's not because you're raising the number before it to that power. It's because it's raising 10 to that power. So 6.022 times 10 to the, and then we want to go 23. And now if you press enter, it's just going to spit it back, because otherwise it'd have to spell out this entire number that was on the screen earlier. That guy right there. And they don't want to do that. And it's just a very angry number. So they're going to simmer it down that way. On the TIs, you can force it into scientific notation. Most scientific calculators have a mode now where you can force the calculator into scientific notation always. Even if you were to put, and I'll switch mine to science. Even if you were to put the number 1, hello, quit, thank you. Even if you were to put the number 1, it'll convert it into scientific notation saying 1 times 10 to the 0. Well, 10 to the 0 is 1, so this becomes 1 times 1, which is 1. And so that's the way that works. If you want to do any kind of calculation with this, the calculators can handle it just fine. I have seen instruction. I don't like it, but I have seen instruction in books or manuals for calculators where they like to go times 10 and then raise that to the 23rd. The other 23rd, the kind with a 3. Thank you. And then that's what they want to use. Now, initially it looks just fine. The problem with putting it in this way is the calculator will read this as 6.022 times 10 to the 23rd. The times will be in there. It reads the order of operations in it. If you use the E, it sees 6.022 times 10 to the 23rd as one single number. So it treats it as one whole number, not two numbers being multiplied in a sense. This comes into play when I want to, let's say, I want to divide. So I want to divide 6.022 times 10 to the 23rd by Planck's constant, which is 6.626 times 10 to the negative 34. Well, if I want to divide those, and I would normally go 6.022 hello, man, apparently I cannot hit anything today, times, and then this magical 10, and then we have exponent 23. Wow, I'm going to guess it's just because my pointer is not functioning just ever so. Divided by 6.626 times 10 to, I don't need that, to the negative 34. All right, now let's go ahead and think about this for just a moment. I'm taking a very large number, very large, and I'm dividing it by an extremely small number, one that's less than 1. If you take a number and you divide it by something less than 1, it's going to get bigger. I'm expecting a number that should be bigger than this. And if you just take the 10s and ignore the 6s, you call that 1 for all I care. 6 divided by 6 is 1. We'll call it 1. Anyway, if you take a look at this, 10 to the 23rd divided by 10 to the negative 34, I should have to subtract those. So it's 23 minus negative 34. That should give me somewhere around positive 57. If I press enter, though, you notice I don't get anything near that. That's because of the order of operations. If you use this particular notation, you have to put each one of the numbers in parentheses. Or you can skip it all together and just put 6.022 E and then 23. Ugh, wow, 23 divided by 6.626. Now we cheated, remember, we cheated and said that this is roughly 1. It's not going to be roughly 1. It's a 9 point something, so we're just going to, it's going to be 9 point something times 10 to the 56 instead of 57. But it'll be close. It'll be really, really close. And then we have this, and we say time negative 34, and we hit go. So this is much closer to what we thought we should get, which is 1 times 10 to the 57. Yeah, all right. It's within times 10. It's close enough. So as you can see, there's a huge difference. Highly, highly recommend you deal with the E. Use the times 10 to the key. There's one on there somewhere. Little $10 calculators, the Scientifics, they're just going to have them right there on the face of the button. Otherwise, you'll probably have to hit a little shift key or something. All right, I hope this helped you write out scientific notation. Take care. Good luck.